Now we can look at another important aspect of a magnetic circuit, right? Which is magnetic hysteresis, right? And when it comes to magnetic hysteresis, we try to understand it by looking at what? A plot of magnetic flux density against magnetic field strength, right? So we call this curve the BH curve. With the BH curve, this illustrates the relationship between what the magnetic flux density and the magnetic field strength, as you can clearly see here from this example. So think about it this way. Imagine you have your material, let's say iron, and with the piece of iron, you count wires around the iron, right? For example, this way, have your iron, and you have wires being coiled around this, so that you have a number of 10 of the turns, and then you have currents, and this being equals to the magnetic field strength equals to Ni over the length. So we have this way, and we have a piece of iron. So you can see that if I have current passing through this piece of iron, then I can calculate the magnetic field strength, right? And you can see magnetic field is then proportional to the current. So if I want to vary the magnetic field strength, I can just increase the current, right? So you have an example of this nature. Now, what tends to happen is that you realize that when you are increasing, you can vary, in that case, the magnetic flux density, right? And what tends to happen is that you can increase the magnetic field strength, and you reach a point whereby upon further increment in the magnetic field strength, there's not going to corresponding increment in the magnetic flux density. In other words, you reach a saturation point, meaning you reach a point whereby upon increasing the magnetic field strength, the magnetic flux density will still be the same thing. That's what we refer to as the saturation point. So at that point, which is here, we can get the maximum magnetic flux density, right? So this is our saturation point. Now, with this saturation point, you realize, okay, I'm no longer increasing the magnetic flux, right? Density. So you start to reduce the current, right? So you reduce the current till you get zero current, meaning now you are no longer having magnetic field strength, right? Which is zero. But what happened is that you realize that the magnetic flux density of the material is not going to be zero, right? It will go to retain a kind of magnetism, right? It will still have some magnetic field. So that is what we refer to as retentivity, right? So retentivity is simple, the ability of the material to maintain, right, its magnetism, meaning its magnetic field, whenever the magnetic field strength is zero, right? So if the magnetic field strength were to be zero, and you still have some magnetic field on your material, referred to as the retentivity of that material. And different materials are going to have different retentivities because of the nature of each of these materials that are out there. Right? Now, we now at magnetic field strength is zero here. So you get retentivity. If you now continue to decrease the magnetic field strength by reversing the current, right? So that it will be in the opposite direction, so that you get negative values. So if you do that, you reverse the current, meaning you are reversing the magnetic field strength. You reach a point whereby the magnetic flux density is going to be zero, right? So the magnetic field strength required or needed to make the magnetic flux density zero is what we refer to as the coercive force, right? So in other words, it's a force that is needed. In this case, that's the magnetic field strength needed to make the magnetic flux density become zero, right? And we use call the HC, right? Now with this, we can continue to increase, and then the magnetic flux will rise and then reach a saturation point again. So we have the saturation point here too. Now, upon increasing the magnetic field strength, you still get the same magnetic flux density. Then you can reverse the current again, and then you start to increase it, right? So here you start to increase again at zero magnetic field strength. Then you still have retentivity, meaning you have your retentivity. You still have some magnetic flux density in your material. Then you can keep on increasing the magnetic field strength. Then at some point, you get again a zero magnetic flux density. So that is still going to be our coercive force, right? Then we increase the magnetic field strength again. The magnetic flux density rise to the saturation point. And then you have this, right? So you end up having this too, right? So by having a material and then you are passing current through it, it goes through this circle, right? Right, this circle. So then this forms a loop, right? That's why we refer to this as the hysteresis loop, right? The area associated with this loop here is going to give us the energy loss of the material, right? The energy loss. And energy is going to be lost, or is going to appear as appear in the form of heat. So the energy loss here is going to be the form of heat. Then once I know the area of the loop, that means I know the energy loss of the material, right? Of the material. Now that we have an understanding of hysteresis, so when we talk about hysteresis, right, in general, we are just talking about the lacking effects, right, of the magnetic flux density whenever there's variation in the magnetic field strength, right? So with that lacking effect, it's what we refer to as hysteresis, right? And this is the hysteresis loop. And you can see that different material will have different loops, right? Because depending on the material, right, the kind of ferromagnetic material, we have hard ferromagnetic material and the soft ferromagnetic material, right? And when we talk about the saturation point for each of these material, you see that will also going to depend on, again, the nature of each of these material. So let's say I have a material of this nature, and we know that within each of these material, we have magnetic domains, right? We have magnetic domains in each material, and the direction of this magnetic domain, they tend to disoriented, right? They are not really organized in any way. When we are dealing with a pure or a natural material, right? If I have iron in its purest form, is going to have its magnetic domain are going to disoriented. And when you are passing current through it, try to magnify the material, then these dipoles are going to begin to align in one particular direction. So you can see clearly here, I have iron here in its natural form, the domains here and disoriented. I indicate that by the arrows, right? The arrows are facing anyhow. But once you are increasing the magnetic field in them, this will start to align in one particular direction. When all this magnetic domain in the material align in one particular direction, that will give it eightfold magnetism, right? And at that inside, you find the saturation point of the material, right? So this is what magnetic hysteresis is all about. If you want to know more about this. And then any other topic relating to apply just make sure you subscribe and then share this video with your friends and colleagues so that they also benefit from it. See you in the next video. Bye bye.